you today. I want to start a brand new chapter, and I want to talk about probability. Now, if you'll recall, the last chapter that we discussed was counting concepts, and we learned how to count using the multiplication principle, combinations, permutations, basically to find out how many things something involves. Well, we'll use some of those same concepts to discuss probability. But before I can really get started, we need to go over some definitions. The very first one is deterministic phenomenon, and that is something that can be predicted exactly on the basis of obtainable information. So if you can find the information and that means you know exactly what is going to happen, then that would be deterministic phenomenon. And an example, the cost of produce when you check out. So let's just say we go to Walmart and we buy some broccoli. Well, the price is right there. So it costs so much per pound. You buy a head of broccoli, you weigh it, and you can expect how much it's going to cost. That's how much it will cost. So that's what we mean by deterministic phenomenon. It's something you can research. You can find out exactly what to expect when something happens. On the other hand, random phenomenon. This is a value that cannot be predicted exactly with obtainable information. An example of that might be the customer demand for the produce, or if we use broccoli, right? We can't predict customer demand all the time for that broccoli. So that might change back and forth from week to week, from day to day. Now, there are ways to model customer demand, but you can't predict it exactly by just looking something up or finding out some information. So you have deterministic phenomenon and random phenomenon. Then you have probability, and probability is the likelihood that an event will occur. So speaking of random phenomenon, say a basketball game. He's playing in the Final Four. That's a random phenomenon. But now there's a probability that certain teams will make it to the Final Four versus other teams, right? But it's still a random phenomenon. You can't determine exactly who's going to be there. And so probability would determine the likelihood of a particular team being in the Final Four. All right, experiment is an observation or measurement of a random phenomenon. So when you do an experiment, you figure out, you get some information to help you determine how likely it is for something to happen. An outcome is the possibility. So for example, speaking of a basketball game, the outcome is, say, this team will win or the other team will win. That's the only possible outcomes of a single game, right? Either, UCLA will win or Michigan will win. I just grabbed random teams offhand there. Okay? Now, a sample space is the set of all possible outcomes. So, like I said, if UCLA is playing Michigan, then the set of all possible outcomes is either Michigan will win or UCLA will win. And then an event. An event is a subset of the sample space. Remember, the sample space is the set of all possible outcomes. So an event is a subset of this, and another way to think about it is a particular collection of possible outcomes. So we'll often be looking for the probability of a particular event occurring. Does that make sense? Now, speaking of event, there it is again, the definition. You could have what's called a favorable outcome. And these are outcomes that belong to that event. And we'll discuss this when we do problems. A success is really another way of saying favorable outcome. So often we'll say, if the coin landed on heads, that might be a success because that's the outcome we're looking for. An event has occurred. It's any time a success is observed. So this is the language we'll use when we're talking about probability. So the probability of an event is determined in two ways. And then we'll get to finally do a problem. So let's talk about the two ways a probability of an event is determined. One way is theoretically. Using mathematics, we've already come to an idea of what the probability of something happening is. And I'll give you an example of a theoretical determination of probability. And then the other way is empirically, which is with an experiment. Sometimes you don't know the probability of an event occurring, so you run an experiment to find out what might be more likely or what the probability of a particular event happening is. Okay, so let's do an example, and we'll talk about theoretical probability and empirical probability. Okay, so first example, here we go. Finally, right? If a single coin is tossed, okay, so we're just going to toss a single coin, find the probability that it will land tails up. So let's think about this. First of all, pick a coin, any coin. Let's grab a quarter, right? It's a little bit bigger than the other coins. So we're going to toss that coin. Help me out first with the sample space. So what is the sample space? What could happen when we toss the coin? Well, we could get a heads, and I'm going to use H to represent heads, or we could get a tails, right? Nothing else could happen. I guess it could land on the edge and stay that way, but I have never ever seen that happen in my life. I mean, it's going to really land on heads or tails, and that's just all there is to it. Now, if you have a real quarter or a real government-issued coin, it is weighted so that it can land on heads or tails that's equally likely, is what we would say. It's not going to land on heads more often than it lands on tails. As a matter of fact, you could think of half of the time, or 50% of the time, it's going to land on heads, and the other half of the time it's going to land on tails. So, you could say the probability that it will land, look, we're looking for tails up, the probability that it will land on tails is 1 chance out of 2 options, right? There's 2 possibilities, and tails is one of them. So it is a 1/2 probability that the coin will land tails up. You could also say that's a 50% probability. Why? Because 1/2 is 50%. As a matter of fact, 1/2, you know these things, 1/2 is equal to, if I change that to a decimal, that's 0.5, right? 1 divided by 2 is 0.5. If I change that to a percent, remember you move the decimal 2 places to the right. So 1, 2, that would give me 50%. All of those things mean exactly the same thing. I prefer the fraction unless it says your answer should be in decimal form. So that's our very first probability question. Now for our next question, question B, if a plastic cup is tossed, find the probability that it will land on its top. So what do I mean on its top? Right there. So it's going to land on the part that you drink out of. Now, this is not like tossing a coin, right? Matter of fact, I even say it right here. It's not like tossing a coin. We need more information. I mean, is it going to land on the top as often as it lands on the bottom? And I would think if I throw this thing or toss it, it's probably going to land on its side, like a lot, right? I mean, if you just toss a solo cup around, it's probably going to land on its side. So we don't really know these probabilities ahead of time. That might remind you of one of our definitions that we talked about, right? Let's keep going. How am I going to know what the probability is of it landing on its top? Well, maybe we need to perform an experiment. And what I ought to get you to do is go out and get you a solo cup and start tossing that thing and tell me how many times it lands on its side, how many times it lands on its top, and how many times it lands with the bottom down, just like you were going to drink out of it, right? We would do that experiment. Now, do we want to toss it just a few times when we do the experiment? Or do we want to toss it a bunch of times? What do you think would be most accurate? Probably if we toss it a bunch of times, right? So let's assume I did this for you already. Consider an experiment of tossing the cup 50 times. That's a pretty many times. So let's say it landed on its side 44 times. Seems reasonable. It landed on its top 5 times. And it landed on the bottom 1 time. These numbers seem pretty reasonable to me. I didn't actually do this experiment. The book did the experiment, but I thought, okay. But now if you want to do your own experiment, let me know. I'll be glad to change these numbers. All right, now here we go. Now, remember the question. It says, find the probability that it will land on its top. So I'm going to highlight that information for you. It landed on its top 5 times in our experiment. So when I calculate the probability, then we would say 5 times, ooh, it disappeared on me. Let's try this again. How about 5 times out of how many times did I toss it? I tossed it 50 times. So the top number is how many times the event occurred. Okay, and the bottom number is the total number in the sample space. So we tossed well, not a coin, we tossed the cup 50 times, and so that's the total number in the sample space. Now, anytime you get a fraction as your answer in probability, or really anything in mathematics, you need to reduce it to lowest terms. So 1/10 is the probability. In other words, 1 in 10 times will this cup likely land on its top. So basically, upside down, like this, except the cup is not a cone. There we go, upside down. Kind of getting the hang of this? Now I got a question for you, right here. Considering the last 2 examples, do you think the probability was determined theoretically or empirically? So let's go back and remember our examples. Remember, the first example was tossing the coin. That was theoretically, right? I didn't do an experiment to determine if this coin was going to land on tails half the time and land on heads half the time. That's what coins do. They are evenly weighted where they should land on tails or heads half the time. If you toss the coin 100 times, it's going to be real close to 50 times on heads and 50 times on tails. So that is, remember which one it's called? You go back and look. That's called theoretical probability, right? It's determined theoretically. So let me write that down for you right here. This is the coin toss. On the other hand, the cup, we used empirical probability. Why? Because we didn't have any information about how that cup is going to land, so we ran an experiment. And if you run an experiment, you're talking empirical probability. Now, we will revisit this idea later on, but I wanted to go ahead and point that out right off the bat. Now, considering the last, we already did that, right? Theoretical probability. Here we go. Here's the formula. Now, notice I kind of threw out how to calculate probability without giving you an official formula. Now I'm giving you the official. But before I was just basing it on information you probably already know about probability. It says if all outcomes in a sample space S are equally likely, just like tossing a coin, and E is an event within the sample space, just like getting tails, then the theoretical probability of an event E is given by the following formula. The number of favorable outcomes divided by the total number of outcomes. And notice they put N of E. Remember, N means the number of, so the number of favorable outcomes just means the number in the event. That's what the E stands for. And then the number of total outcomes, they put N of S because that's the number in the sample space. All right, now for empirical probability, it says if E is an event that may happen when an experiment is performed, then an empirical probability of an event E is given by the following formula. So once again, probability of E, that's that first notation. Now, the numerator is the number of times the event E occurred, just like our experiment with the solo cup, divided by the number of times the experiment was performed. So remember, we did 10 out of 50, because the event was it landing on its top. That happened 10 times, and the experiment was performed 50 times. All right. You ready to try another problem? Here we go. So Kathy wants to have exactly 2 daughters. Okay? Assuming that boy and girl babies are equally likely, find her probability of success for the following cases. So this is like 2 separate problems. So we'll do problem A first, and then we'll do problem B next. All right, so let's just first look at problem A. So she has a total of 2 children. Now, before you can do a probability problem, you really have to think about the sample space. what's going to happen? What could possibly happen? Well, first of all, she has 2 kids. So her first kid, let's draw a tree diagram. I can't say it. So what's the outcome of her first child? Well, it could be a girl, right? Or it could be a boy. I'm not digging that G a whole lot. Let me try it again. So a girl or a boy. Now she has a second child, right? Well, considering if her first child was a girl, she could once again have a girl or a boy. And then if the first child was a boy, she could have a girl or a boy. Now, if I list the sample space, all the possible outcomes, we could have a girl, then a girl, right? We could have a girl, then a boy, or we could have a boy, then a girl, and then a boy and a boy, okay? Where the first letter is the first child, and the second letter is the second child, right? That's the whole sample space right there. So, notice what we're trying to find. Exactly 2 daughters, okay? Find the probability of its success, which is having exactly 2 daughters. Now, remember the denominator is the number in the sample space. How many possibilities are there altogether? There's 4. There's 4 different possible outcomes. A girl and then a girl and then a boy and then a girl, and a boy and then a boy. Okay? Now, how many of them meet Kathy's request to have exactly 2 daughters? Just the one, right? So 1 in 4. So your probability is 1/4. If you change that to a decimal, it'd be exactly 0.25. But always leave it as a fraction in lowest terms unless it says change it to a decimal. Now let's try example B, right? So again, example B was the difference. So Kathy wants to have exactly 2 daughters. Okay, assuming that boy and girl babies are equally likely, find her probability of success if she has a total of 3 children. But once again, she wants exactly 2 daughters. So I need space. Let's do this one in pink for the 2 daughters. So for B, let's first of all find the sample space. We could have a girl and then a boy, at least Kathy could. And then for her second child, she'd have a girl, a boy, a girl, a boy, but she's going to have 3 children. So for her third child, she could have a girl or a boy if she had a girl and a girl. Or she could have a girl or a boy if she had a girl then a boy. And then she could have a girl or a boy if she had a boy then a girl. And then finally, she could have a girl or a boy if she had a boy then a boy. Now let's write down our sample space, right? So S is equal to, and you got to follow the line. Girl, girl, girl. And then girl, girl, boy. Now go down here, girl, boy, girl. And then girl, boy, boy. And then down here, boy, girl, girl. And then boy, girl, boy. And then we have boy, boy, girl. And boy, boy, boy. Is that all of them? Now, one way you could tell is you could look at your branches and just count the ends. So 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 possibilities. 1, 2, 3, 4, 5, 6, 7, 8. Yes, I have all 8 of these listed. All right. So the probability, remember, you always divide by the number in the sample space. So there's 8 possibilities. Now, how many of those possibilities are exactly 2 girls? Now, girl, girl, girl is not exactly 2 girls. That's exactly 3 girls. So girl, girl, boy is 2 girls. Girl, boy, girl is 2 girls. Boy, girl, girl is 2 girls. And I believe that's the only ones that have 2 girls. I'm checking them. Yes. So what do we put? Well, there are 3 successes is what we would call that. Okay, I'm sure that Kathy wouldn't call it unsuccessful, but if she wants exactly 2 daughters, then these other guys that I don't have highlighted really are not successes. But that's 3 out of 8. We would reduce that if we could, but we can't, so that is the probability. Okay, so example D, find the probability of being dealt each of the following hands in a 5-card poker. Use a calculator to obtain answers to 8 decimal places. Okay, so really we can't fit all 3 of these on this one page, but I want to talk to you about, let's just talk about the first one, a full house. And there's a lot going on in this question, by the way. So a full house, by definition, is 3 of one denomination and 2 of another. Now remember, we learned counting techniques to figure out how many possible 5-card poker hands there are, and we may have even calculated a full house. Not together, I don't think we did, but you probably did in homework. So let's talk about it. So first of all, the number of poker hands, period. Okay, so the number of 5-card poker hands. Now remember, you're choosing 5 cards. How many cards are there to choose from? 52, if you'll recall. Now, are we replacing the cards? Well, no, because you have 5 cards in your hand. You don't pull one out and put it back in the deck. Okay, does the order the cards are dealt to you matter? No, because when you pick up the 5 cards, you can arrange them in whatever order you want when you look at them. Okay, so this is a combination. So combination, we have 52 cards. We're choosing 5 of them. Now, to remind you quickly of the formula, that is 52 factorial divided by 5 factorial, also divided by 52 minus 5 factorial. And you can just type that in your calculator. It's a rather large number when you calculate it. It's 2,598,960. That's the total number of hands. So when we do this calculation, that's our denominator. Now we need to calculate a full house. Now don't stress, because I'm about to show you the way they wanted you to do this problem in the textbook, but I want to discuss this. So a full house. So 3 of one denomination is in a full house. So you're talking about, what does that mean? 3 of one denomination, like a 4, and a 4, right? And then 2 of another denomination, like maybe a king and a king. That would be a full house. So I know that needs to be clear. So if we were going to count the number of possibilities for full houses, so like to get our 4s, so first of all, we've got to pick how many different ways could we pick this value right here. Remember, there are 13 different cards in a suit. So we need to do a combination of 13, choose 1, because we've got to pick, do we want 4s or 5s or 6s or 7s? So that's a possibility. And then, after we pick, whether it's going to be 4s or 5s or 6s, then we need to take our suits. Remember, there are 4 possible suits, and we have to pick 3 of them out, because that 4 might be a hearts, that 4 might be a diamond, and that 4 might be a spade. You see what I'm saying? So that's the 3 cards. And then let's do the same thing for 2 cards. Now when we do the 2 cards, we don't have 13 to choose from anymore, because we've already used up maybe to build our 4s. So we're going to have a combination of 12, choose 1. Okay, so that might get us our kings, or it might be queens, or it might be aces. Okay, and then we have 4 suits to choose from, and we're picking 2 of them. And this is a multiplication, because we need this to happen, and this to happen, and this to happen, and this to happen. And that gives me a value of, when you calculate all that, 3,744. So to calculate the probability of a full house, you take the number of full houses, which is 3,744, and divide by the number of possible poker hands, which is 2,598,960. Okay, I'm going to revisit this. Now, it says we can write that as a decimal. Wow, 8 decimal places? Okay, I'll just do whatever they say. So out to 8 decimal places, that's what we'll do. I probably never wanted that accurate, but anyway. Now, I showed you the hard way to do this. But in the textbook, let me show you something. There we go. Look, they give us a chart that tells us all the different types of events in poker. I mean, it's not everything that can happen, but it's the things that are winners. So a royal flush, a straight flush, 4 of a kind. Look, there's our full house right there highlighted in red. Now, remember, we calculated that. But that's the number. So to do number 1, a full house, there's 3,744 possible full houses. Look, the total in blue at the bottom divided by 2,598,960. Now let me type that in my calculator and find out what the answer would be to 8 decimal places. So 3,744 divided by, again, this big number, 2,598,960. And to 8 decimal places, I get 0.00. It's really low. 144. Now, that's 1, 2, 3, 4, 5 decimal places already. I need 3 more numbers. 058, because I have to round up. So that would be that answer. Okay? Now, the 2 pairs, we could calculate that just like we calculated the full house. But look, all the information we need is right there. And 2 pairs, where is it? I saw it. There it is. Look, in blue now. 2 pairs circled in blue. So that happens 123,552 ways divided by this same denominator, 2,598,960. And once again, I'm just going to type that in my calculator. So 123,552 divided by 2,598,960, and I get 0.0475. 390. How many is that? 1, 2, 3, 4, 5, 6, 7. And then next is a 1 6, so I have to round that to 2. There's 8 decimal places again. Okay. Okay, so for part 3, we're looking at the probability of finding 4 queens, or being dealt 4 queens. So if we use correct notation, which notice I didn't use correct notation there, so let's be formal about it. So the probability of being dealt 4 queens. Notice I'm writing to the far right here because I can't get the pen to write on the left over here, so I'm going to have to squish this in. Now if you check over here in your list, 4 queens doesn't show up. You will notice that it says 4 of a kind. Now I can calculate it using that value. I'll show you that, and then I'll show you the way that I thought about it. So 4 of a kind means we have, 624 4 of a kind, but only one out of 13 of those is all queens, right? Because 4 of a kind could be 4 aces, or 4 2s, or 4 3s, or 4 4s, or 4 10s. Do you see what I mean? And there are 13 different possibilities there. So I would have to multiply 1 over 13 times the 624 divided by the 2,598,960. And you will get the same answer as if the way that I thought about it. Now, when I thought about 4 queens, let's just think about how many ways can you get 4 queens, okay? So think about your 5 cards sitting here. 4, 5. Now, how many queens are in the deck? 4, right? Because there's a queen of hearts, there's a queen of diamonds, there's a queen of clubs, and there's a queen of spades. So you have a queen of hearts, a queen of diamonds, a queen of clubs, and a queen of spades. So there's only one way to get 4 queens. That was my first thought when I first did this problem. But you know what? This 5th card could be anything in the deck except what? Well, a queen, right? We used them all up. So there's 52 cards in the deck, right? We used up 4 queens, so that means there are 48 possibilities of hands, right? Because there's one way to pick the 4 queens, but there are 48 different cards that could go with those 4 queens. And so the way I thought about the problem, instead of 1 over 13 times 624 over our big old number, I thought about it is there's 48 different hands that have 4 queens divided by 2,598,960. Okay, well, turns out 13 goes into 624 48 times. So this is the same calculation, but just two different ways of thinking about it. The way the book thought about it was the first way I showed you. The way I thought about it was, hey, there's 48 different hands because you use up 4 queens, but there's 48 other cards that 5th card could be. Now when I type this in my calculator, I get a really small decimal. So 48 divided by 2,598,960. I get, let's see if I can write it right here, 0.0000. Remember, there's a 0 before that. And then 1847. There we go. So that is the probability of getting 4 queens. Now I should ask you, out of these 3 different questions, what has the highest likelihood of happening? What has the highest probability? We are looking for the biggest number out of our 3. So you have 0.00144, 0.0475, and 0.00001847. Well, 2 pairs, okay, that's this one right here, is the highest probability out of the list. You have a better chance of getting a hand with 2 pairs in it. The next best chance is the full house, because notice that's 0.00144. The lowest chance out of all of these is getting 4 queens. As you can imagine, that would be a pretty tough deal, right? To have 4 queens and some other random 5th card in the pile. Notice again, the probability is 0.00001847. That's 1,847. And what even places that in? Tenths, hundredths, thousandths, 10,000, 100,000ths, millionths, 10 million, 100 millionths. So 1,847 100 millionths chance of getting a hand of 5 cards that has 4 queens. Okay, I'm going to wrap up the first video here, and then you can come back for the second video to finish up this section on basic concepts in probability. I hope you have a wonderful day.